Hi everyone, so this is a review for Chapter 8 Revision Quiz, Set 2. So for this time, we will be discussing question 1, 2, 3, 5, 6, 8, and 11. These 8 questions. Is that 8? This 7? I'm not sure, but yeah, there's questions. Let's move on to the first question. So first question, question 1. You have a uniform beam. Uniform means by the mass across the whole beam is constant. And this beam here has a length of 4 meter. Then the weight is represented by the symbol capital W. Then it rests with one end P on the floor. Well, they are mentioning this part over here, one end on the floor, and point Q is on a smooth hemisphere. This is point Q. Okay, then the distance between point P and point Q is 3 meter. Means by along the plank from here to here, it will be 3.0 meter. Okay, the beam makes an angle of 30 degrees with the ground. Well, there's a lot of words. Let's just zoom out a bit and look at the diagram. Well, that's point P. Your uniform beam is resting on the ground at point P, whereas for point Q, it's resting on a smooth hemisphere. So there should be no friction over here. So they also tell you that the distance between P and Q will be 3 meter. And the beam makes an angle 30 degrees. Well, those are the details. So the force F on the hemisphere on the beam is, so they are asking for this particular force here. What is its magnitude? Well, let's just start with a free body diagram as usual. So for this case, you have a bar that looks something like this. Then because it's uniform, therefore you can know that the weight comes from the middle of the beam. So this is the weight of the beam. And you ask yourself the following questions: whether there's any strings cables, no. Whether there's any force being explicitly stated, yes. So there's a force being explicitly stated, and it should be perpendicular to the bar. It should be perpendicular to the bar, because if you have an hemisphere and a bar, the force should be in a direction tangential to this circle. Not tangential, I mean normal to this circle. So your tangent is here, your normal to the tangent means 90 degrees to the tangent, and you find this force. So it's pushing the bar upwards. So yes, this is the direction. But the important thing is you should know that it's 90 degrees. After that, is there any other force? Well, I believe since you are resting on the floor, there should be probably some kind of reaction force pointing this way. Okay, so now they ask for this force over here. They ask for the magnitude of this force over here. So if you want to find the force, and we have three things here, we know that we will use the sum of torque equals to 0 here. Well, when you usually see when the rigid body is in equilibrium, you relate it to sum of torque equals to 0. So the next question to think about is, where should you put as your axis of rotation? So there's usually people can pick between this point, or this point. So which point will be appropriate? Like I said in the previous video, you pick a point where the information is irrelevant. You don't have the information, and the information is irrelevant. Well, if you see in the question here, they express F in terms of W. That means by you're finding F is relevant. You want to express it in terms of W, that's relevant as well. So that makes our reaction force not really relevant for this situation. If it's not relevant and we don't want to include this thing in our calculation, so what can we do is we assume this as our axis of rotation. Now, by assuming this point P here as our axis of rotation, we essentially remove we remove the reaction force from our sum of torque equals 0. Okay, so after we pick our axis of rotation, let's label the distance. Okay, they mentioned here that this bar is 4 meter. Okay, probably use yellow. This bar here is 4 meter. So that will mean by this part here is 2 meter. So if this part here is 2 meter, then the next thing we can know is this will be 1 meter. This part will be 1 meter. Why is it 1 meter? Because it tells you the distance of Q from P is 3 meter. So that's the information that you have. So with this limited information, you are able to determine the distance of W from the axis of rotation. You are able to determine the distance of the force from the axis of rotation. So everything is clear. It's time to do some substitution. So we have weight. This weight will be turning in this direction, and that will be a clockwise. So clockwise, we assume it to be negative. So negative weight, I'll just write it as capital W because there's no other W. Then times the distance from the axis of rotation, which is 2 meter. Then plus another torque, which is the torque due to this force by the hemisphere of the beam, this F here. So you have your force, and oh, I haven't cleared things out. I write the force, I write the distance, but I forget about the angle. Well, it's very important to remember the angle. So what's the angle? Well, if you know that, okay, I'm off color. Okay, if you know that this is 30 degree, then that will be 60 degree. Okay, if you know that will be 60 degree, then you know that this will be 30 degree. So knowing that this is 30 degree, we will know that the component will be cosine 30 degree. Okay, it will be sine, it will be cosine, not sine. (30°) and follow up with f 3.0. Yes, it's 90 degree, nothing to worry about. So after that equals to 0. So this W times 2.0 times cos 30 degree, we flip it to the right hand side, then you move things around, then it equals to F 3.0. So now you can see that F will be equals to W 2.0 divided by 3.0 cos 30 degree. So now we end up with our answer being 2 over 3 W times cosine 30 degree. So that's our answer for question 1. That's all for question 1. Moving on to question 2. Okay, question 2 mentions that you have 1nx. Okay, let's just zoom out. Okay, 1nx, which is this n over here, and 1nx of the heavy rod of weight W. So this heavy rod has a weight of capital W, and it's hinged to a wall. Okay, it's hinged to a wall at this position X here, and the other end is attached to a cord. Okay, a cord, you can think of it like a string. Okay, one end pivoted to the wall, then the other end is connected to a cord which is fixed at Y. Okay, Y is at the opposite side of the wall, opposite wall. So they mention very clearly that this rod is in equilibrium. So it's not moving, it's not rotating. I mean, it's not accelerating or not as angular accelerating. So which of the following is the direction of force exerted by the wall on the rod at X? So it's hinged onto the wall, right? So it means that there must be a force here, but you're not sure where the force should be pointing towards. So let's try to figure it out. Again, let's start with drawing the free body diagram. You have your object here, then this object here. It's because it's a uniform rod, then the weight will be coming out from the middle. the weight of the rod. Then there will be tension going up this way, okay, and there will be a reaction force, but you're not sure where the reaction force should be pointing towards. Well, now, okay, let's put a question mark here just to remind us that there is a missing force. So we need to label which direction is this missing force pointing towards. Well, how? Okay, so the thing is, there's usually a simple way, a rough way. Okay, it's not a sure win kind of way. It's by checking sum of f equals to 0 and sum of fy equals to 0. Okay, what do I mean? What do we mean? If you look at sum of fx equals to 0, means by if you have something pointing to the right, there must be something pointing towards the left, or else you can't cancel it out. So if you see only one thing pointing to the right, that means it's not in equilibrium. You need another thing pointing to the left to balance it out. So in this situation here, if you resolve this force here, this force actually has a component which is pointing in the x direction. Of course, it's also having a component pointing in the y direction. A y direction is not much of a worry, because this t tension in the y direction, even though it's pointing upwards, it can be balanced by the weight of the rod pointing downwards. So we can safely assume that it's okay, there's nothing wrong here. But if we look at the x direction, we have something pointing to the right, but there's no forces pointing to the left. If that's the case, then the sum of fx will not be equal to 0. So what can you infer from here? You actually can know that the reaction force over here will actually have a component which is pointing in this direction. But now you are not sure whether Ry is in this direction or Ry should be in this direction. So that's what you might be worrying about. So if that's the case, what should we do? Well, actually there's another way which I mentioned in the previous video. All three forces, if you extend the line towards the front, towards the back, they should intersect at a common point. Okay, they should intersect at a common point. Let's just use back the diagram here to illustrate what I try to say. Okay, so you can see that the weight is going in this direction. If I extend this line, then yes, this is the line because of this weight over here. Then you have tension over here. If we extend it to the front and we extend to the back, then you see that it actually intersects at this particular point here. So it means by the next force over here should also, since it's the force being exerted at point X, this force here should actually be crossing this line as well. So it means by this force here, because of the hinge, should be along this line as well. Okay, so let me extend it to the front, to the back, something like this. Okay, so this is the direction of the force at X. But the question we need to answer is whether it's pointing in this direction here or it's pointing in that direction here. Whether it's pointing this direction or that direction, both of them, if you extend the line front and back, it will still come back intersect this common point. So both of them, if you use this deduction method, both of them are still valid. But there's only one correct answer. So you have to choose whether it's this one correct or this one correct. How do we determine it? We come back to the first thing that we determine. We know that it must have an x component pointing to the left. So for this case over here, you see that if we point it upwards, then you have your x component which is to the left. Whereas if you use the second option pointing in the fourth quadrant, then you will find your x component pointing to the right. With that being said, we can safely cross out this one because we want our reaction force in the x direction to be pointing towards the left. Therefore, this will be the correct answer. Then if this is the correct answer, we need to find the vector which can represent this direction. So xy, let's go through one by one. Xy will be pointing. Okay, let me clear all this. Okay, we know this is the thing that we want to find. So let's see which one abide this thing. Okay, the first option that we have is xy. Xy is in this direction. Well, it's a no. We want something which is in this direction. This is correct. Okay, we need to find which vector can represent this. So this one is wrong. Exact. Exact is from x to z. It's exactly opposite to what we want to find. So it's actually still wrong. Okay, the next one will be yx. The next one will be yx. Yx means by it will be something like this. Okay, everything should be come out from this point. So yx, the vector will be pointing in this direction. Point in this direction. Therefore, you shift this vector over here. Point in that direction. Still incorrect. Okay, yx is incorrect. So we are left with zx. Zx is pointing from z towards x. Means by the vector is in this direction. If I shift this vector up, it's exactly the same as the direction that I'm looking for. That's why the answer will be zx. Okay, so that's all for question 2. Let's move on to the next question. Question 3 asks about a beam. Then this beam has a weight of W, capital W, and it hangs in equilibrium. Again, if you see equilibrium means by sum of torque equals to 0, sum of force in the x direction equals to 0, sum of force in the y direction equals to 0. Okay, this beam here is supported by two chords. One chord is XP, another chord is YP. There are two chords over here and they are connected, okay, at this point P over here. Okay, the tension is T1 and T2 respectively. So now they ask for a comparison between the magnitude of weight, the magnitude of tension 1 and magnitude of tension 2. Well, it's something that we never discussed in class before, but this is actually related to something you learn in SPM. Okay, in SPM you learn about a concept called the triangle of forces. Okay, what does the triangle of forces mean? It means by when an object is in equilibrium, what will happen to the object if it's in equilibrium? All the forces, you can shift it until it forms a loop. Okay, you have probably seen something like this before. You have your weight, then because of your tension, then you have tension 1, then you have tension 2, something like that. Okay, you see that the arrow must flow in a circle. Okay, it points downwards, it flows, it never resists each other, so it flows in one direction like this. Okay, if you follow the arrow, it flows in one direction. So this is what we call as a triangle of forces. Why when an object is in equilibrium you see this triangle of forces? Because if you resolve this thing, you see that the x direction of T1 and the y direction of T2, okay, this is T2, and the x direction of T2 will cancel each other out. They are in opposite directions, so they cancel each other out. And T1y over here if you add it up with T2y over here, T1y plus T2y, you see that it's equal to W. That's why these three lines, if you shift it properly, it will form a closed triangle. The triangle can be formed. It's closed because they're in equilibrium. How much x you have in this force, the other forces must have enough x in the opposite direction to cancel it out. Same for y. If you have y this much pointing downwards, the other forces must have enough y pointing in the opposite direction to cancel it out. Okay, that's the idea behind triangle of forces. So in this case, you can actually construct a triangle of forces as well. You just need to know how to shift it. Okay, so if you shift it, what I usually do is I usually put the vertical line first. Then I try to imagine how to make the other two lines fix. Okay, you see this one, it's pointing towards the left up. It's pointing towards the left and it's going up. So reasonably, you can draw it like this. Okay, T2. Then you have your T1 which is going up and to the right. So you can close up the triangle with something like this. Okay, so in this triangle of forces, the length of the force vector represents the magnitude of the force itself. So we can see here, the weight here is actually the longest line. So that means the magnitude of the weight will be largest. T2 here, okay, if you see here, T2 here is bigger than T1. T2 is bigger than T1. Therefore, T2 have a larger magnitude compared to T1. But both of them are still smaller compared to W. So with that, we can construct an equation which we set W as the maximum. Then T2 will be after it, followed by T1, which is the smallest. So with that said, we can say our answer is this. Okay, if you're not constructing the same triangle, you're constructing a triangle that looks something like this. You start with T1 going upwards first. Then you follow it up with T2 pointing like this. That's also a valid triangle. As long as the triangle cycles around in the complete cycle, not conflicting in terms of direction, then it's a valid triangle of forces. As you see, T1 is still shorter compared to T2. So everything still follows. So our answer is still correct. It's still valid. So that's all for question 3. Let's move on to the next question. Question 5. What will happen to the rotation of Earth if the ice cap at the North Pole and the South Pole melts and water produced flow towards the equator? Well, this is an interesting question actually. But if you can get the idea, it's actually a relatively direct question. Okay, so this is my Earth. I pretend this to be my Earth. So, well, I have ice caps in the North Pole and I have ice caps in the South Pole. Okay, now they talk about these ice caps melt. So if the ice caps melt, then it means by this ice cap is no longer here. This ice cap is also no longer here. So where did it go? It flows towards the equator. So if it flows towards the equator, means by it's flowing towards here. Okay, same for the other side, the South Pole as well. So they flow towards the equator. So what does it mean? So the water right now will be probably spread around this area here. Okay, this is just a rough idea. So your water should be probably around here. So how does it affect the rotation of the Earth? Well, if you are rotating something, there must be an axis of rotation, right? So if we call this our axis of rotation, before the ice cap melts, most of the most of the water here are actually close to the axis of rotation. It's close to the axis of rotation. It's close to the axis of rotation. But now, if the ice caps melt, then the water will flow towards the equator, and the equator will be further away from the axis of rotation. So instead of saying like this, let me give you a top view. Oops. Okay, so this is a top view of the Earth. Okay, if you view from this angle, draw an eye. Okay, if you view from this angle, then you will see initially, if this is our axis of rotation, this one is our axis of rotation, then you see that the ice caps are actually near here. These are the ice caps. But after that, if the ice caps melt, what you will see after that will probably be something like this. It will no longer be here. What happened is it's moved towards the equator. So equator will be further away from the axis of rotation. So your water is now further away from the axis of rotation. So you learn about moment of inertia. If moment of inertia, it's basically sum of mi ri squared. So if this distance from the axis of rotation increase, what will happen is your moment of inertia will increase. So if your moment of inertia increase, you learn about principle of conservation of angular momentum. So sum of Li is equals to sum of Lf. So initially, if you have this I and this omega, when the ice cap melts, what happens is your moment of inertia increase because the mass is now further away from the axis of rotation. So you now have a larger moment of inertia. What will happen? Because you want to equate left hand side and right hand side, the angular velocity, okay, the angular velocity will have to be decreasing. You have to get a smaller angular velocity in order to balance the whole thing out. Smaller angular velocity means by a slower rotation. So slow rotation, you can say that the speed of rotation decreases. So this is our answer. Speed of rotation decreases. The moment of inertia actually increases, and this one is wrong. The rotation kinetic energy is out of your syllabus. Okay, so that's all for question 5. Let's move on to the next question. Question 6. A toy train travels along a track fixed to the rim of a wheel. Okay, there's a wheel, then you have a track which is fixed on the rim, fixed to the rim of the wheel. Okay, let me draw this out. Okay, let's say a wheel probably have 2 layers, right? Usually. Okay, so this is your wheel. So what you do is you install a track. Okay, let's say a track in green. So install a track which is near the rim of the wheel. Okay, so this will be my track, and the toy train will be moving on this track over here. Okay, this is your track. This is not me shading area, it's like a toy train track, a train track. Okay, so your choo-choo train will actually move on top of this thing. Okay, so now the mass of the wheel is greater than the mass of the toy train. So let's write it out. The mass of the wheel is greater than the mass of the toy train. So with that said, initially both the train and the wheel are at rest. Okay, nothing is moving, everything is stationary, and there is no external force. When you see there's no external force, you have to alert yourself that this is an isolated system. So you probably do something regarding to conservation of something. Okay, so when the train starts to travel around the track, the wheel will rotate how? Okay, so this is an angular principle of conservation of angular momentum question. Okay, how does it work is you have your initial angular momentum equals to the final angular momentum. So initially you can see that the train and the wheel are at rest, no external force. So it means by, okay, let me zoom this out a little bit. So it means by you have your initial angular momentum for the wheel and you have your initial angular momentum for the train. Okay, and of course you still have two objects at the final condition. You still have two objects. So you have your wheel final and you have your toy train final. So because initially both of them are at rest, basically you can't have angular momentum. So this will be 0, this will be 0. Okay, then the next thing they tell you is the train starts to travel around the track. So let's imagine this train probably moving in this direction. So it asks how will the wheel rotate. Okay, let's say if the train is moving in this direction, so let's call this direction positive, a positive direction. So you have your moment of inertia. Okay, we keep the wheel not sure because we don't know much about the wheel. Just I of the wheel, omega of the wheel final. Then we plus the I of the train, moment of inertia of the train, and moment of inertia of the angular velocity of the train final. So if you are having this case, and what can we do now is we want to find the ratio between angular velocity of the wheel and the angular velocity of the toy train. So what can we do is we probably shift this to the other side. Brain is not working very well. And this one will be here. Train final. So if you want to make a comparison between the angular velocity, then we will do something like this. There's too many curly things here. Okay, then I will left with IT and negative I of the weight. So they tell you this is the equation that we arrive from the principle of conservation of angular momentum. But from here we can actually extract a lot of information already. Okay, they mention here that the mass of the wheel is greater than the mass of the toy train. So if the mass of the wheel is greater than the mass of the toy train, it's very likely that the moment of inertia of the wheel will also be greater than the moment of inertia of the toy train, because toy train is really very light compared to a wheel. So if that's said, we can say that okay, let's shift it in a way that's easier to understand. IT will be smaller than IW. Therefore, in this case, IT is up here, IW is down here. IT is small, IW is large, means by this will be a value less than 1. Okay, I mean you ignore the sign first. So IT is small, IW is big, so you see this will be a value less than 1. So if it's a value less than 1, then our angular velocity of the wheel will be equals to IT over I weight, wheel, sorry, then you have your tire final. So what does this mean? If this is less than 1, then what does it mean is the angular velocity of the wheel final will be less than the angular velocity of the toy train final. What does this mean is it's rotating slower. So the tire is rotating slower compared to the toy train. So rotating slower, we can already say that the train and the wheel will have a smaller angular speed. So if it's smaller angular speed, then this will be correct. Oops. This will be correct. This will be correct. And the next question to ask is, what's the negative sign for? The negative sign shows that this omega of the wheel will be in the opposite direction as the omega of the toy train. Opposite direction, that's why you have a negative. So it means that one of them will be clockwise, one of them will be anti-clockwise. You have to determine which one is clockwise, which one is anti-clockwise. It's not mentioned in the question. So the important thing is they are in opposite direction. So opposite direction, well, we have our answer. Our answer is in the opposite direction with a smaller angular speed. Okay, so that's all for question 6. Let's move on to the next question. Question 8 here says that you can safely Question 8 here says that you can safely stand on the overhanging end of a heavy plank that rests on the table. Well, that's a mouthful of word. What does it mean? Okay, what does it mean is actually, if you have a table, let's assume this as a table. Okay, then we also assume table should have legs. Okay, table. Okay, what does it mean that you can safely stand on the overhanging end of a heavy plank that rests on the table. So heavy plank that rests on the table means by you actually have a plank that is resting on the table. But something interesting here is that there's an overhanging end of this plank. So this is the overhanging end. And this overhanging end, you can safely stand on it. Okay, you can safely stand on the overhanging end of the heavy plank. That's what it means. So how far out depends on your mass and the mass of the plank. Yes. Okay, if this plank is more massive, probably you can stand, this overhanging end can be longer out. If it's a very light plank, then probably you can't have a very long overhanging end. So it's something logical. So it depends on your mass. If you are heavy, well, it will turn. Okay, the plank will just turn. Okay, so suppose you can stand on the end of a plank that overhangs the edge of the supporting table 1/4 of its total length. Okay, so this is again a difficult sentence to understand, but what it means is you stand on the end of a plank, and this end of a plank overhangs the edge of the table. Okay, this is the edge of the table, and it's 1/4 of its total length. Means by 1/4 of the total length it's overhanging, 3/4 of the total length is resting on the table. Okay, at L. Okay, so now they ask how massive is the plank compared to your mass. So how do you solve this problem is, first you need to understand, so this is a person, maybe this is you, you are standing on the overhanging end, then this length of the overhanging end is 1/4 of the whole length of the heavy plank. It means by 3/3 of the length of the plank is resting on the table. So with that said, we need to draw the free body diagram. Well, for this free body diagram, it's a bit tricky because as you can see, you have plenty of surface touching here, plenty of touching surface here. So it's a bit difficult actually to draw the free body diagram, but you can think of it another way. Okay, so let's start with the first thing. You have your weight. Your weight points down from the center, the weight of the plank. Then the next thing is there any strings? No. Is there any external force being explicitly stated? No, I can't see any. But you know that there will be your weight of the person right here. Okay, let's call it U, because weight of U. This is the thing that we have. Then last thing is we have contact surface. In this case, we don't think the friction is relevant, so we focus only on the normal force. So where should the normal force be pointing at? I mean, it's quite, you can safely assume it's pointing upwards. The table, of course, it's pushing the plank upwards. But should we draw the normal force pointing upwards from here, or from here, from here, or from here? So now that's a tricky question to think about. But if you remember from our practice in where we did this practice before, in your chapter 8 we draw a free body diagram which looks something like this, and I demonstrated in the video as well. If this person is massive enough, then this thing will almost want to turn. So when it almost want to turn, nearly wants to turn, you see that it is pivoting on this particular point here actually. Okay, you see the plank actually pivots on this particular point here. Okay, so this is actually the place where you should draw your normal force. Okay, but of course we don't assume the plank is inclined right now. The plank is horizontal, but you need to know that when this person is massive enough that this plank almost want to turn, you know that it will have a hinge around here. You can treat this place as the axis of rotation. So we are looking at that specific moment actually, the moment where it almost wants to turn. So in that case, this is the only place which is in contact with the heavy plank. Therefore, your normal should be pointing upwards from here. Okay, if you cannot understand, probably you should review the chapter 8 question that I demonstrated in YouTube. Okay, so now this is what we know for now, nothing else. These are all the forces. Let's label this as normal. Okay, so now we want to, what do we want to do? We want to determine the mass of the plank. Okay, you want to determine the mass of the plank when compared to your mass. Okay, so again, it's the same thing again. You need to do sum of torque is equals to 0. And you need to pick a point to choose as your axis of rotation. It's either this point, or this point. But as I said, you pick the point which is irrelevant to you. You want to compare the mass of the plank with respect to your own mass. So this is relevant, this is relevant. So what is not relevant? This is not relevant. The normal by the plank, by the table on plank is not relevant to you. So you pick this as your axis of rotation and you label the distance of all the forces from the axis of rotation. Well, we know this is 1/4 of the length, and we know this is half of the length because weight come down from the center. Therefore, we can safely also assume that this is 1/4 of the length. Okay, so if we do sum of torque equals to 0, then it will be the weight of the plank times 1/4L that will be anti-clockwise, it's going in this direction. Whereas for this weight of u yourself, will be going in the clockwise direction. That's why weight of u will have a minus sign in front. So with that said, I believe you can see the answer already. Wp 1/4L is equals to W of u, the weight of u, times 1/4L. So we cross out, then you're left with the weight of the plank is equals to the weight of u. That's why the answer is the weight, the mass of the plank is the same as your mass. Okay, so this is how you prove the situation. I believe if you understand the situation clearly, then this should be a solvable question. So that's all for question 8. Let's move on to the next question. Okay, question 10. If the polar ice caps melt, the resultant water will spread over the entire Earth. The new mass distribution will tend to make the length of a day. Well, the answer is longer. The explanation is in the previous question. Well, here it says the water spread over the entire Earth, but it's the same idea. Previously, your mass is concentrated near the axis, but if you really follow the situation given in that case, then if you refer back to the top view, the water spreads over to the whole place, right? It means by every place here would see a lighter spread of water. So before that it's concentrated here, now it's spreading out. If it's spreading out, then the distance will be further away from the axis of rotation. Therefore, the moment of inertia increase, that will cause your omega to decrease. Okay, because omega decrease, you cause your period to increase. Why? Because from here to here, you want to keep L equals to I omega, and you want to keep the L constant. That's why the omega will decrease. Then why omega decrease cause the period to be increasing? Because of omega equals to 2 pi over t. Means by if omega decrease, your period will have to increase. Increase in period means by the length of the day will be longer because it's rotating slower. That's why you see sunlight for longer time. That's why the length of the day is longer. Okay, so that's for question 10. Let's move on to the next question. Question 11 says you have a forces which act on a uniform rod, and this uniform rod has a weight of 4 Newton and length of 40 cm. Okay, so let's just straight away draw the rod first, just in case I forget about it. So you have your rod, and this rod is 40 cm, and it says here it has a weight of 4 Newton. Then now this rod is free to rotate in a vertical plane. Means by it can rotate something like this. You can see it rotate like this, or you can see it rotate like this. Well, any particular method I'm not sure about, but now it is in equilibrium. Okay, it's asking for at which situation the rod is in equilibrium. So to fulfill this situation, you need to achieve 3 conditions again. Sum of torque equals to 0, sum of fx equals 0, and sum of fy equals to 0. So now let's look at the combination one by one. Okay, so if we pick combination 1, then you will see 2 Newton going up, 2 Newton going up. Then you will see this weight is 4 Newton. So you can see if we pick this point as our axis of rotation, we fix it as this point, then you will see that the torque produced by this force is balanced by this torque produced by this force. They have the same magnitude of force, and they are at the same distance away from the axis of rotation. So the magnitude of the torque produced by this will be the same as magnitude for this. But because this one is an clockwise torque, whereas the other one is an anti-clockwise torque, basically they will cancel each other out. So you can see that this is achieved. There's no x direction force, so it's equal to 0. For the y, up is 4 Newton, down is 4 Newton. Achieved. Yes, that's why your answer is A. If you look at option B, both of these torque are clockwise torque. This will make things turn clockwise. This will also make things turn clockwise. So they will not be in equilibrium. Whereas for this one is also, all of them are anti-clockwise torque. This will make things rotate this way. This will make things rotate this way. So both of them are anti-clockwise torque, then they will not cancel each other out. So not in equilibrium. This one also not in equilibrium because 2 Newton plus 4 Newton, 6 Newton, they are all pointing down. Then you add on another 4 Newton pointing down. So for that case, your sum of Fy cannot be balanced because all the forces are pointing down. There's no upward forces to balance it out. So D is also not the answer. Therefore, your answer is this one, A. Okay, so we have discussed 8 questions continuous. Yes, that's the next set. We have discussed 8 questions. So that's all for chapter 8, set 2. Thank you very much.